There we go. So recording has started. Welcome to this course that we do on a yearly basis. It's related to PVT and phase behavior and Whitson Plus specifically. My name is Matthias Carlson, and I'll go through the course today with you all. If you have any questions, just feel free to unmute at any time or use the chat in Teams as well. This course, probably compared to a few of the other courses that we're running every year, is a little bit more theory and less software. And some of the other courses are like almost only software and less theory. But it covers a lot of very fundamental things that has an impact on essentially every single thing you're doing in a software like Whitson Plus. It's very good to be on top of those things and be aware of them. So for the course today, just a little bit of general information. The first thing is we're believers in making it practical. So hopefully all the things that you're learning today, you'll be able to also utilize and kind of conceptualize already, today in Whitson Plus on your own wells. And we also believe in repetition, such that the things that is very, very key and important are things we'll repeat several times throughout the slide deck today. And hopefully at the end of it, at least you've covered a few of those things or you bring home those and you hopefully never forget them. So it's around 3 hours today. Hopefully it can be interactive. So if you have any questions, just ask them in the chat or on mute. And of course, the digital material is sent out after the class as well. Some of the content that you'll see in the slide deck, that's more meant for reference for later. So you can use it to if you're sampling a well or whatever, you can go back into the slide deck and use that as a reference. The other thing, just as a quick disclaimer, is that this is more tailored for practitioners, so people who need PVT properties on a day-to-day basis, but not necessarily kind of PVT experts. So if you want a really, really in-depth PVT equation of state modeling type of experience, we have another course for that. Very good. The handouts that we provided are the slides that we're going through here. You also should have gotten access to courses.whitson.com, and I'll also send out some of this written material off the course today, just in case you want to read upon more of the things we're talking about today in more of a paper form. Again, I think most of you have logged into Whitson Plus already. If you haven't, go to courses.whitson.com. Use your username and the password right here. So your username will be your email. Remember, this is a public course, and I know everybody on this call has access to Whitson Plus on a day-to-day basis through their own domain. But make sure that you, in this, at least for the exercises we're going to go through today, that you use courses.whitson.com. The course contents that we're going to go through and the way we kind of structure the course today is to kind of follow what we call the PVT value chain, if you like. So we're going to start with petroleum fluids. We're going to then go and sample those petroleum fluids. We're going to send those to a laboratory. And then we're going to develop a model and use that model in engineering calculations. And this is really where you as an engineer will spend most of your time utilizing these PVT models in day-to-day work, whether that's for reserves estimation, RTA, could be PTA, simulation, bottom of pressure calculations, you name it. So we have a few course goals today that we hope to kind of get through with you all. And the first basic one is that hopefully at the end of the course today, all of you will have kind of a rigorous way of classifying reservoirs into black oil, volatile oil, near critical fluids, gas condensate, wet gases, and dry gases. And that's important because I think there's still, just see that from a lot of support tickets that we're getting, that's still a little bit of confusion related to, you know, what is a gas condensate, what is a wet gas, and whatnot. So that's going to be great to clarify. We also want to understand the difference between what we mean by an in situ representative sample and a reservoir representative sample. We also would like to conceptually understand what an equation of state model is and what the inputs are. So not necessarily develop one, but conceptually understand it. We also would like to be able to predict PVT data from readily available data and an equation of state model. And then we would like to be able to learn how to initialize a shale well using readily available data, for instance, GOR. So before you're going to run any type of calculation on the well, every single well needs to have a PVT estimation. We also would like to be able to estimate PVT properties at initial reservoir conditions. So for instance, formation volume factor, etc. And we also would like to learn how to calculate oil in place and gas in place numbers using this type of PVT. And in the end, we would like to be able to generate the PVT table and also understand the most important pieces of a PVT report. So there's a lot of good stuff here, a lot of information. So that's a reminder for myself as well that we're going to take some breaks. We're going to try to at least take a 10-minute break between each of the hours here. If this is the first time you're attending a PVT course, then I'll send out this after the course. It's actually a really nice 2-3 page document written by Curtis actually back in probably before I was born, and he wrote that for AAPG, so kind of PVT for geologists. So most of the important terms, proper definitions, etc., could be found in that document. But the key parts for you when it comes to PVT, and you hear PVT is one of these acronyms that's thrown around in the day-to-day, if you're at least a reservoir engineer, so you're working with reserves or whatever. Like, yeah, do you have, you know, what's the PVT? And what does that really mean? Like when someone comes to you and say, okay, what's the PVT? Well, what it really means is the physical and thermodynamic properties of gas and oil. And that's kind of how we're going to treat it in this course as well. And if you think about that, the what we do commonly in oil and gas is we refer to those physical and thermodynamic properties as PVT, and that's relating to pressure, volume, and temperature. And one of the simplest equations we have for that is this equation we have to the right here, which is called the ideal gas law. And as you see there, it relates pressure, volume, and temperature. So a very fundamental equation. And it's actually one of the most simple equations of state that we'll get back to later. Another question we get a lot here is like, oh, well, but we also produce water. And that's right. So we'll touch a little bit upon water as well. The reason why water typically isn't spent too much time on in a PVT course is that it's a little bit simpler from, call it, a complexity perspective. And the water properties, so particularly density and viscosity, is primarily a function of salinity and the reservoir temperature. So it's not super complicated, doesn't have that much hydrocarbons in solution, etc. So, but we'll cover it a little bit, and we'll also talk about when water PVT is important. But before we go there, we're going to talk a little bit about vocabulary. And there's a few terms that I'm going to say that we talk about every single day here at the office, but then I realize if you're not kind of doing PVT stuff on a daily basis, that you that might be different for you, or that will be words that you maybe don't use on a daily basis. So I'll just cover those one time, and then next time you hear it, at least it's not the first time you hear about these words. And the first term that I'm going to use is an equation of state model, an EOS model. That's a thermodynamic model. The second term I'm going to cover is the compositions, then flash, K values, representative samples, and then this term called solution CTR, or vaporized oil ratio. And I'm just going to cover these one time, and then you'll see it throughout the material, such that once you see it the second time, hopefully it's not as great. So we'll start with the basics. We're going to start with the first one, what is an equation of state? And before diving into the details, you can think about an equation of state model as if you want a very simple way of thinking about it, think about it as a correlation, if you like. And it takes in three inputs, takes in temperature and pressure. And temperature and pressure, they're two inputs to an equation of state model that we can relate to in the day-to-day. So I live in Houston, for instance, and in Houston today, it's not super warm. So I have a relationship to what the temperature is when I go out. And if you are in a kitchen, you know, you have a pressure cooker in the kitchen there. So you also can relate to pressure. The last thing that's an input here that's a little bit more abstract for people is this input called composition. That's this guy here at the top, okay? And in a composition, that's just the amount of different molecules that makes up a fluid, okay? So the simplest way to think about what a composition is, if you would like to have kind of if you want to have kind of like a black oil version of that, you can think about that as a GOR or CGR, okay? So if your temperature and pressure and your GOR is changing, then your PVT properties will change. So that's how you know, if you want to think about the inputs to an equation of state, you can simplify it into that. And once you have those inputs, you can predict any type of PVT properties: viscosity, compressibility, saturation pressure type, etc. Okay, these are just a few examples here to the right. And I want to double click on this item called composition, because that is a word I remember when I did. So I was one of Curtis Whitson's students back in the day, and in university, I hadn't done chemistry, I remember, in high school. So when I was in his classes, every time he mentioned this word composition, I just like got so confused, and I couldn't remember the last part of the sentence. But what is a composition? Well, a composition is just the amount of different components that makes up a fluid, and it's usually expressed in terms of mole percent. And we all often dictate different types of fluids with different symbols, if you like. So if you talk about a liquid, we typically use the symbol Xi. And we typically use the color green, and that's an SBE standard. For vapor, we typically use the color red, and we also use the symbol YI. And then if you talk about a total composition, like what we call a total well stream composition, for instance, the reservoir composition, we use the symbol ZI. Okay, so like an example there will be at surface, you have a gas composition, that will be a symbol YI, and then you have a liquid composition with a symbol Xi. And if you want to bring this into your day-to-day, okay, we know the composition of air. It's primarily nitrogen and a little bit of oxygen. We know the composition of sparkling water. It's primarily water and a little bit of CO2 and maybe a few other things. And the petroleum fluid is just a more complicated version of that. If you're dealing with oil, you can actually have thousands and thousands of isomers making up that fluid. If you're dealing with a dry gas, it will primarily be methane and a few of the non-hydrocarbons and a few of the lighter hydrocarbons. Okay, so that's one of the inputs, and we'll see how you can easily predict what these petroleum fluids are. When you use an equation of state and you have an equation of state and a composition, we hear this word flash all the time, and we say that we flash the fluids to surface, to the separator conditions or whatever. We took the oil and we flashed it to surface conditions, and of course the flash is neither of these. The flash, I don't know if people remember the Flash player, always just like nightmares or horror on a daily basis. I haven't watched this other movie, but that's neither of those guys, but it's this thing that we call a two-phase isothermal flash calculation. And that's often used in vapor-liquid equilibrium calculation. And what it does is that it takes this fluid that we're producing, so let's say an oil, to, for instance, the separator, and we equilibrate at those conditions, and we get a equilibrium vapor phase with a certain composition and a liquid phase. So when I use the word flash here today with you guys, just think about that as like, okay, I take this fluid and I stabilize it, if you like, or at some kind of conditions, and it separates typically into two phases, or sometimes it can even remain single phase. And just a very simple example of that is if I took an undersaturated fluid, I flashed that at the saturation pressure, so that's the bubble point. Well, then there will be a little bubble of gas coming out of solution. That's what we call the incipient phase. And if I lowered the pressure even further and did a flash, then I will get a stabilized gas phase and a stabilized oil. And what dictates these flash calculations right here is what we call K values. And K values, those are equilibrium K values, and that's essentially what an equation of state comes in and generates for you. So you can think about an equation of state almost like as a K value generator. So it tries to generate K values for you, and those K values dictate whether a component would like to be in the oil phase or in the gas phase. So when you run the calculations in Whitson Plus today, or if you run calculations in general in any software that's equation of state based, it will generate those K values, and K values will dictate for each of those components that you're dealing with, whether that's methane or CO2 or nitrogen or whatever, will that component like to be in the oil phase or in the gas? Yeah, so if you look at the K values, they represent the relative preference of being in either the gas phase or the oil phase. Okay, so if you take a component like methane, there's an example here to the right, love to be above 1. Okay, always likes to be in the gas phase. And then a K value less than 1 typically likes to be in the oil phase. If you take a very heavy fluid, for instance, like C30 plus or something, loves to be below 1. So very simple context in that, or concept in that perspective. So this is kind of in layman terms. The fifth thing that we need to talk about, because there's a lot of confusion around this, and this is maybe one of the few slides you would really like to pay attention to because it might be new. And this is when we talk about PVT, we talk about this term called representative samples all the time. The fluid was representative, it was not representative, but we need to have some very, very strict and clear definitions of what we mean by being reservoir representative or in situ representative. So that's what we're going to do now. We're going to have very clear definitions of what those two words mean. And a reservoir representative sample is any uncontaminated fluid sample that's produced from the reservoir. And that is automatically representative of that reservoir. An in situ representative fluid sample, that's a sample that's representative of the original fluids in place. So what happens here many times is that people think that a PVT sample that is, for instance, sampled not at the original GOR of the well can't be used for anything, okay? But that's not right. And the accuracy of PVT data has nothing to really do with whether you are in situ representative or not. You can have an extremely in situ representative fluid sample, which means just, okay, you sample before the GOR goes below the bubble point, but all the PVT data can be rubbish. And vice versa, you can also have a PVT sample that you gathered after the well went below the saturation pressure. The GOR was now 2,000 instead of 1,000. Okay, it's not in situ representative, but the PVT data is still has a lot of value, and many times that PVT data can also be of really high quality as well. So accuracy of PVT data has nothing to do with whether the sample is in situ representative or not. And God forbid, don't throw out any PVT data that has been sampled at a GOR that is not in situ representative, because you can still use it to create a model. And just to simplify, or like to exemplify this, if we look at this as an example of a well, if you just think intuitively on it, this is an unconventional well. The GOR is changing from day one, goes from 1,000 up to 4,000. And we want an equation of state model that's representative for all times, not only in the beginning, not only at the end, but for all times. So if you create an equation of state model, you want to make sure that that equation of state model, or that correlation, or whatever you want to think about it as, predicts every single type of fluid that you are dealing with over time. And in these unconventionals, we see all kinds of fluids. So that's what we mean by an in situ versus a reservoir representative sample. So just some examples then, like, okay, what would actually be, if you think about what samples you should use, well, a sample that's sampled as long as it's not mud contaminated and it's done above the saturation pressure, that will be both an in situ representative sample and a reservoir representative sample. A sample that's sampled below the saturation pressure will not be in situ representative, but it will be reservoir representative. And a multi-contaminated sample will not be either in situ representative or reservoir representative. Last term that we're going to cover, and these are kind of the advanced terms, and hopefully it'll just get easier from here. But when we talk about a term that's really relevant for a lot of these unconventional reservoirs, it's this term that we call solution CGR, or vaporized oil ratio. And this term right here quantifies the condensate in solution with the reservoir gas phase. Okay, and I'd like us to step back there for a minute. So if you think about if you have a gas phase in the reservoir, in which cases can you have a gas phase in the reservoir? So when will this be relevant? Well, an obvious one is for a gas condensate reservoir that is a gas phase both above the dew point and below the dew point. So that's an easy one. The other one is a wet gas. A wet gas will not have a dew point in the reservoir, but it will carry liquids with it to the surface. So it's relevant there. And it will actually also be relevant for oil reservoirs. And that might be something that is not intuitive for everyone here. But the reason why it's also relevant for oil reservoirs is that once the oil goes below the bubble point, gas comes out of solution, and that gas can have a lot of condensate in solution. Okay, so it's relevant also for oils, and it's more relevant for like a volatile oil and an air critical oil, obviously, of two reasons. First of all, there will be a higher RV value, and it will also be more of it, so because more gas is coming out of solution. So it's important for two reasons. The units of it's barrels per million, and the symbol for it, SBE calls it as little RS, so they refer to it as solution CGR or OGR. In the industry, we typically call it RV, so vaporized oil ratio. Okay, and we use kind of both interchangeably throughout the course today. And if we pulled up the software, if I just made if I went to my project right here, I'm not going to do this exercise now, but I'm just going to show you. This is an oil reservoir, but it has a solution CGR curve right here. Everybody sees that. It's a low value, and it starts to become relevant from here and down. So this is what we call solution CGR, and we use both terms, RS or little RS and RV. Okay, so that's this condensate term. Also relevant even for a fluid like this. That's a black oil, and we'll talk about that in a second. Excellent. Okay, so hopefully now we've actually gone through, and you know, it's like in the morning, we've already gone through the most difficult stuff, the first 30 minutes, and it's just going to be downhill from here, as we say, at least in Norway for people that love skiing. But I don't know if there's any questions so far. It looks like so far so good. But if there are any questions, just feel free to shoot them in the chat here. Before we're going to take a quick break, we're going to continue for around 20 more minutes, and we're going to cover some PVT fundamentals. And my goal here from the beginning of the day today until we get to 12, at least here in Houston, is to make sure that you have some of these fundamentals at your fingertips, and that when you use the PVT or the PVT in Whitson Plus or in any other software, that you have a little bit better understanding of what matters, why it matters, and also when it matters. So the reason why PVT is important is that PVT is probably one of the very few things that has an impact on every single discipline in the petroleum domain. Whether you are a reservoir engineer doing reservoir simulation, whether you do RTA or PTA type of analysis, whether you do pipe flow, process or facility designs, or you do reserves, it's relevant. It's relevant for a lot of other things too. Even when you drill, PVT is important. So we know PVT is an input to a wide range of disciplines in the petroleum domain. And a very key concept there is to understand that when we talk about a barrel or when we talk about a cubic meter in PVT context is not always a cubic meter or a barrel, doesn't matter. And what do we mean by that? Well, what we mean by that is, of course, volumetrically, the volumes are the same. The amount, so the mass, density, composition, and monetary value is different. And I'd like everybody here on the call to take 15 seconds. I told you I was in a world where gas was not worth anything, which is a lot of places. And I wanted to maximize how much money I make, would you take a reservoir barrel, a separator barrel, or a stock tank barrel? Just think about it for 15 seconds. Which one would you pick? It's very core to this this concept of PVT. Obviously, in that context, everybody would like a stock tank barrel because a reservoir barrel would shrink to stock tank, a separator barrel would shrink to stock tank, and the stock tank barrel, you know, that's already shrunk. That's at the reservoir conditions, or that at the conditions that you are selling the fluids. Okay, but it's the same volume, but of course not the same composition, mass, density, or monetary value. The second thing that's really important and interesting here is like not only do like a volume in a PVT perspective, they have a context, right? This is a context. It's reservoir barrels, or it's separator barrels, or it's stock tank barrels. It has not only a context, but it's also a function of the process or the path to get there. And that's the second key thing when it comes to PVT, is that PVT properties, they're process dependent. And what does that mean? Well, it means that the final product volumes, they depend on pressure and temperature conditions and the path to get there. Okay, the simplest example of that, that's your GOR and your formation volume factor. If I have a super simple process, those GORs and formation volume factors, they will not be very favorable. And what do I mean by that? Well, if they're not very favorable, that means that your formation volume factor will be higher, your shrinkage would be higher or larger, your GORs will be larger, meaning less of the components goes into the liquid phase. And vice versa, if I invested in a super complicated process like this, I would expect, okay, I paid much more money, that more of the fluids become stabilized liquids. And why is that important? Well, if you take isobutane, for instance, and you put with today's commodity prices that isobutane molecule in the gas phase versus the oil phase, I think there's like a 20x difference for the same molecule. 20x difference, okay? So it definitely matters when it comes to what process you're going through. So are you doing a single stage flash, or is it like a multi-stage process and whatnot? And I'm going to show this just super easy now in the software. And you're not supposed to do this. We're going to do some exercises later. But I'm just going to take a super simple case right here. I predicted the composition, so I'm just going to make sure that the composition in both examples are the same. And I think in this particular scenario, we're dealing with the formation volume factor of 1.38. And I have a two-stage process right here. But what if I removed a stage? I made it less efficient. I didn't invest in that additional separation at stock tank. I just put it straight to stock tank. What do we think is going to happen with our formation volume factor and our GOR? Well, it's the same fluid, it's the same composition. The composition is exactly the same. It's this stuff right here, but now our formation volume factor went up a lot. The exact same molecules we're producing, but GOR went from 750 to 842. And vice versa, I could go in and add more separation stages here, try to make it more efficient, like a more efficient type of separation. And then I would maybe expect that, you know, the GOR goes down from 750, my formation volume factor goes down. And a lower formation volume factor and a lower GOR is good. It means that more liquid, or more of the molecules that you're producing, are going into the liquid phase versus the gas. Okay, and that's what we mean by being process dependent. So when you see the surface process here, it's because it's process dependent. Very good. I don't know if there was any questions. Just let me know. Okay, so this is a key concept in general, and there's not a week that goes by without people asking questions about the surface process. You know, what is the surface process? What does it do? Why is it important? Etc. So now we're going to do the first little exercise here. We have a reservoir fluid right here. This is a reservoir fluid. This is the composition for the reservoir fluid. We have light, intermediate, and heavy. And my question to you is, I would like you to guess, is this a reservoir oil or is this a reservoir gas? I'll give everybody a minute here. So remember, gas here, that's the lighter components here. And we can just assume that the temperature in this case is, let's say 200 Fahrenheit. Okay, so this is all the lighter components. This is the gassy components, and this is the heavy component. Do we think it's an oil or do we think it's a gas? If you want to be good, you can try, like, you know, my guess is to be water, for instance. If someone wants to write in the chat, I'm not forcing people, but try to think about it. You think it's a oil, or do you think it's a gas? So hopefully people have been, and I'm sure some of you guys thought it's a gas versus an oil, and some of you thought it was an oil versus a gas. And of course, it was kind of like a trick question. And this is because we're showing the mole fraction of each of the components. If I flip this and I showed you the mass fraction of each of the components, well, then we would be maybe thinking, okay, 80% of the weight here is C7 plus. C7 plus is the stuff that goes in and makes basically, turns into stock tank oil. That's the heavy stuff. Well, then maybe you would think it's an oil. And we'll learn these rules of thumb later, but this was a trick question, and this is a reservoir oil. And this comes back to a third key point. That's that to understand, really to understand PVT, you need to have an understanding of these components and the distribution of everything that's heavier than C7. And that's what we call heptanes plus. And a heptanes plus is an extremely good correlator to a lot of different type of PVT properties. Here's just an example of GOR versus C7 plus, kind of bracketed into different fluid types. But it's also an extremely good correlator to fluid type in general. So when we build like a rule of thumb type of list, and of course these will be different if you go and look at McCain's book and whatever else, or if you look in SBE or in Schlumberger's thing, but they're rule of thumbs in general. And when it comes to C7 plus, if you tell me what the C7 plus is, it's a very easy exercise for me to estimate what at least I think the reservoir fluid type is. Okay. This is a really helpful slide that we see a lot of our clients are using, and I use it all the time as well to at least have an initial guesstimate of what the fluid type is. And the same goes with the GOR range. Important to emphasize here, a rule of thumb. So if you have a lab report that shows something else than this, of course, then you need to listen to the lab report. A thing that comes up very often is someone has, for instance, a lean wet gas that might be above 100,000, but it has actually a dew point, a very low dew point in the lab. Like that's a very typical thing, and people are like, "Oh, but it should be a wet gas." Well, then in theory, it is a very lean gas condensate. So just things like this. These are rules of thumb, but very good rules of thumb. And again, here C7 plus is extremely key. And we're going to bring this in to the next part here, where we're going to talk about the reservoir fluid classification. And reservoir fluid classification is very important to just have right and make sure you're using the right definitions of it, else it can be really confusing. And I see there is some, people talk about like, okay, what's a liquid rich fluid? Well, that's not a fluid type. Also, rich gas, that's not a fluid type. That's just like a term that people have been using. Liquid rich, what is it? Well, it's not really well defined. So that's what we're going to work on today, to make very, very distinct definitions of different fluid types. Used SBE, of course, guidelines to do that. But most importantly, hopefully you can remember what they are, such that you can have a very constructive conversation when it comes to different reservoir fluids in your asset as well. And if you look at the different fluid types that we have, it's 5 different fluid types. It's dry gas, wet gas, condensates, volatile oils, and black oils. And in between volatile oils and gas condensates, there's the red little dot, we have something that we typically talk about as near critical fluids. They're fluids that's kind of like hard to kind of place whether they're an oil or a gas condensate. But in general, the classification of these reservoir fluid systems, they are determined by 2 criteria. And those 2 criteria are the following. The first is the location of the reservoir temperature with respect to the critical temperature, and what's called a Cree-Connon term. We'll talk about what that is in a second. The second part, which when I learned it, I didn't want to believe it. I was like, that can't be true. And that's the location of the first stage separator pressure and temperature with respect to the phase diagram. And does everybody kind of understand why that's a little bit mind-boggling? It's like here we're talking about a reservoir fluid definition, but the location of something that's happening on surface actually impacts it, if that makes sense. So if I you know, in kind of like a corner case, I could change the definition of a dry gas to a wet gas if I just changed my separator conditions, which at least for me in the beginning was a little bit hard to grasp, but that is how it is. So we're going to go through these. We're going to give you some ranges, or we've already given you the ranges, but we're going to give you some examples and also show you some phase envelopes, and also where this Crecon and term type of criteria is, and how it's used. So we're going to start with the black oil. Black oil, if you look at a black oil and you plot the liquid relative volume, which is this guy right here, and we do that above the saturation pressure, and then we get, of course, one, it's 100% liquid, and then when we hit the saturation pressure, the oil shrinks. So gas is coming out of solution, and if it's a black oil, then typically this line is pretty straight, okay? The shrinkage is pretty straight. So this is where we have a bubble point, okay, up here. You see that we're far to the left, the critical point, and the Crecon and term. And this is what we typically call a black oil. And what we do is we say, okay, everything is a black oil up and including 1,000 scf per barrel. So if you were in Whitson Plus here, I could change the GOR type. So if I change the GOR type to 1,000, you see the same thing. My reservoir conditions far to the left of the critical point. There it becomes a volatile oil in our system. If I made it 999, then we say that it's a black oil. Yeah. So we just put that call it rule of thumb. That's the only one where there's like, okay, you have to pick something, and that's what we did there. Okay. So what's the difference between a black oil and a volatile oil? Well, a volatile oil would typically be closer to the critical point, and typically that will also mean higher saturation pressures, right? So if this was moving to the left and then you move this one to the right, okay, higher saturation pressures, more gas coming out of solution. And the other thing when you look at the shrinkage curve is that your shrinkage curve when you hit the bubble point will be more non-linear, and that's like volatile oil versus black oil is probably the only one where there's a little bit like there's not this super clear distinction between this is a black oil and volatile oil. But if you like, when we look at a PVT report and we get the data, then typically we would, if it was like something we have to give an opinion on, we would just look at the shrinkage curve right here. So the more curvature it is to this, the more of a volatile oil it is. Third fluid type, it's when we go to the other side of the critical point right here. That's what we call a condensate. So now you're in between the critical point and the Crecon and term. And that sounds very advanced to say, but what it really means is a retrograde gas condensate reservoir, that is a reservoir where you have a dew point. That's it. If you have a dew point, you are a gas condensate reservoir. As simple as that. And in fancy terms, it just means that you're in between the critical point and the Crecon and term. And when you plot the liquid dropout curve, of course, you have no liquids above the dew point, and then you actually start to build or drop more and more liquids out. But then this curve is actually non-monotonic, and we'll talk about why it's non-monotonic later. And you guessed it right, it's related to both K values. Well, it's related to K values. So you get this net condensation-driven period and this net vaporization-driven period. So the difference between a wet gas and a gas condensate, that would be that you're actually now to the right of the Crecon and term. Okay, sounds fancy. Matthias, stop using all these difficult words for me, please. Well, what it means is that there's no dew point. And how can you see this like in practice? Well, if you're producing from a well where the GOR is flat, or like quote unquote flat forever, and you're far below well, if it's flat forever and that's not a reservoir effect that makes it flat forever, most of the times then it's a wet gas. Okay. Unless you're producing above the dew point. But as long as you see GOR over time and it has a GOR over 5,000 scf per barrel, then 900,000, and there's like almost every case would always then be a some kind of lean or rich gas condensate. Okay, so if GORs are changing, then must be some kind of saturation pressure most of the time. How does the liquid dropout curve look? Well, it's boring. No liquids for all pressures. And the most important thing here, gas, it can't drop out any liquids in the reservoir, but it has to drop out liquids at surface. And that's the difference between a wet gas and a dry gas, where a dry gas also has no liquids in the reservoir, but it also doesn't drop out any liquids at surface. So it's a gas from the reservoir. That's the difference there. So just to summarize here, before we're going to take a break, if we look at two examples here, we look at a volatile oil. Okay, if we're undersaturated, it's 100% liquid. When we hit the saturation pressure, gas bubbles form and they rise. And then if we stabilize that liquid, you'll have a free gas phase and a free oil phase, that gas phase being more mobile than the oil. If we're dealing with a gas condensate reservoir, the gas condensate reservoir would be the opposite. We'll be looking at this type of curve right here, and we will have oil droplets that will form and fall. And then if we stabilize it here, we'll have a gas and a oil. And the oil there will be typically very immobile in at least many cases, but that depends on the rock. So with that, we're going to take a 10-minute break. We'll be back in 10 minutes. And it's primarily just for my own voice, but we'll be back at 10 Houston time.
Matthias, is this an okay time for questions?
Yeah, absolutely.
A geologist here, so apologies if this is an entry-level question, but going back to when you talked about how changing your separator setup can change your formation volume factor. I'm thinking about when you calculate a formation volume factor, I believe we always try to use surface or atmospheric conditions as what we're kind of solving for when we're looking at how those fluids change from the reservoir to the surface. But I believe I heard you say that you could kind of squeeze out more oil at the surface if you just configured your separator setup a little differently and had multi-phase separation. Is that what I heard?
Yeah, exactly. So in this exercise that we did, in all of these cases, we just added or removed a separator essentially, right? So we added a separator, then we add more money to it, and if we add more money to it, we'll hope that makes us more money in terms of liquids. So that is correct. So the exact same molecules we produce can turn into a different formation volume factor and GOR depending on how you process it at surface. But from like call it a geology perspective, if you're mapping a formation volume factor map for a whole basin, which we help a lot of companies with, then the most important in that scenario would be to make sure you use the same assumption for surface process. Of course, if you go into like every level detail, it won't be 1000% right for every case. But in those cases, it's much more important to be consistent than anything else.
Let's say as a geologist at a company, you're not aware of what the production team is actually implementing in the field on a well-by-well basis.
Yeah.
Can those separator conditions make a meaningful change that can result in what appears to be a bust in an oil in place map, or would it be kind of like a small change and you're not going to notice it?
Yeah, that's a good question. So depends on what or what would be a good example of what like a big error is. But in short, for gas condensate reservoirs and for wet gases, if you're off on the surface process, it can be really significant differences, probably at least 30%. For like a black oil, it will be less of a big difference. So typically up to 1,000 scf per barrel. I'd be surprised if it's more than plus minus 5% in general. And then it kind of increases from there. But in reality, we want to really have a good overview, especially for like a basin-wide mapping or something like this of every single facility. And even the people working in the companies, honestly, want to really know all the details of every single facility. So the better thing to do there is just to have some assumptions that we feel are good default assumptions. This is, for instance, our default in the software. And most of these different basins, they will have some surface process that's more or less representative of what you would see in that basin.
Excellent. Thank you so much.
Okay, we're gonna get started again, and we're gonna go straight to an exercise, which hopefully we're gonna be pretty okay, because now you know everything that you need to know when it comes to different reservoir fluids. And here we have the whole gamut of different fluid types. They're dry gas, wet gas, condensates, near critical oils, volatile oils, black oils. This is from the SPE phase behavior monograph book, kind of the go-to book for SPE on PVT. It's in chapter 2. But there is one mistake in this table, and we need to figure out which mistake it is. So that's the exercise today. From the stuff that you just learned, what is wrong with this table? And that's going to be the starting exercise of this next session. Any ideas? You can write it in the chat if you see it. Okay, a few good ones. I also saw there was a question here about, so the PVT model takes into account the surface process when calculating the composition of the reservoir fluid, as opposed to interpretation of GOR is affected by the separation process. Yeah, so exactly. So the GOR is a function of the separation process. So if you assume a certain separation process and a GOR, of course, that will have an impact on your fluid composition estimate. Back to this exercise, we have a few guesses here, but yeah. That is right, actually. Sheriff had the right answer, and that's that for a wet gas should not have a P set. So if any of you guys have this book, just X this out, and there should be no P set. A better question is like, also some people, a lot of questions like, what's the reservoir temperature here? That is a really good question. Because that, but you know, then I would say like 200 F or something like. But that's exactly right what Sheriff said right there. That wet gases should not have a P set. So easy, but again, back to this thing that, you know, a dry gas has no liquid at surface. Wet gases has no saturation pressure or dew points down in the reservoir, and condensate has a dew point, and air critical fluids has saturation pressures as well. The next thing we're going to talk about, which is very relevant for many of you when it comes to initializing fluids in general, and then this is just an exercise for you to like, okay, when I have a well, for instance, a well like this, and I have the producing GOR over time, what would kind of like, which GOR should I use? If you take a look at these first 100 days of producing GOR, well, it starts up at 1200 and then it kind of stabilizes down here. Which one of these should you use? So that's what this next session is about. And if this was my well, I think the general principle is to go and try to find stabilized, the first kind of stabilized GOR that you have. But in some cases, you're dealing with a GOR that shoots up from day one. So what can you do then? But if this was my well, I would probably go for something like 750 or maybe 775 or something like this. And what could be helpful is to use cumulatives sometimes here. So what we're going to do now is to go through kind of fluid initializations 101. And this comes from that we have done this hundreds and hundreds of times, and I've been working with you guys on trying to find how can we actually initialize these different fluid types. And what we're going to do is we're going to do the same as this guy. I'm not a basketball guy, but I've heard this story that Steph Curry, he practices 500 3-pointers a day. And that's around 200,000 per year, which is just back to this thing that repetition is key. So you need to see it many times to be able to pick it up. And once you kind of learn the skill, you will be able to do this really fast. But a few things that we're going to do when we do this together now, we're going to go through this kind of like visual exercise together, is the first thing we're going to acknowledge is that the producing GOR will tell us a lot about the well. And the second thing that we're going to acknowledge is that in general, that below the saturation pressure, GORs are expected to increase. That's very easy. The other thing is if you have a constant CGR or a GOR over time, then most likely you're dealing with a wet gas. If you're dealing with a dry gas, you're not producing any hydrocarbon liquid. And then a rule of thumb that could be really helpful for you to know about is this 250 barrels per million, 4,000 scuffs per barrel. That particular point right there, that's close to what we call the critical point. And the critical point, that's when it's impossible for you to kind of distinguish, is this an oil? Is it a gas? or is, what is it? And at that point, it doesn't really matter what you call it, because at the critical point, the properties of oil and gas will converge, so that we'll have the same saturation pressure, same GUR, same formation volume factors, same compressibility, etc., etc. So when we are going to go through these different examples, what we will go and do is we're going to start here with a very low GUR oil, and we're going to move up over the critical point, and we're going to end over here. And what you guys are looking at right now is a phase envelope, okay? It's a phase envelope, but it's not the typical phase envelope that you're used to looking at. You might be, we've learned about this type of phase envelope here in school, but this phase envelope right here, that is a phase envelope in pressure composition space. And we learned about an equation of state has three inputs: pressure, temperature, and composition. In this case, composition is kept constant and we vary temperature and pressure. Temperature. Here, we're keeping the temperature the same, but we're varying the composition, which is the GOR, and the saturation pressure. So this is essentially how a black oil table actually looks like under the hood. So we're going to start pretty easy. We're going to start with one black oil, and I'm just going to flip through these pretty quickly, and you can again use them as a reference material. But again, we will start here with like a 400 scuff per barrel, 300 scuff per barrel fluid, and go further up here just to look at these examples of how we would actually initialize these in practice. So we start with this around 300. So for this case, it has a lot of noise, but initially here we see some kind of stabilized period. So if this is my well, I'll pick a GUR close to 300. This is another example, another easy one with around 400. And then as we move forward here, we're seeing another example with 600. Here we would probably pick the stabilized region here and ignore the period before. This is a 750 case. I think actually this is the case we're looking at right here. Yeah, exactly this case. And here we'd go for around 775, probably the what we would go for around here. Again, these are fairly easy because they're black oils with no saturation pressure. This is another case around 1,000. Again, ignore this period in the beginning. The reason for it is that that's typically a cleanup period, and a cleanup period, then you haven't your ratios haven't stabilized yet. So most likely what you're producing is not representative of initial of in situ fluids in the reservoir. What happens when we move higher and higher in our GORs? Naturally, if I increase this from 750, so basically, if I took this example right here, this is 1,000, and if I just increased, oops, that was 200. If I increased it from 1,000 to 2,000, we see our bubble points are increasing. And what really happens is that we're moving our conditions here closer to the critical point. So that's also what happens here on these different examples that we have in the slide deck. As higher the GOR becomes, then the higher the saturation pressure also becomes. And all of these have pretty clear, all of these are real wells. They have a stabilized portion of the data initially that you would like to try to honor before you hit the saturation pressure, and then GOR starts to shoot up. And these are other examples of the same thing. Again, here we're getting up in the 1800 range. This is very noisy data. And again, when you're dealing with noisy data, what can be super helpful is to just use the cumulative GOR option right there, just to smooth out that type of information. And you can also flip to the OGR version as well if helpful. Okay, now we're getting even closer. 2,000, 2,500, 3,000, 4,000. That's essentially here at the critical point. So that means that most likely this is like a near critical fluid in general. And if I went in and actually put in 4,000 for this well right here, you see how close I am to the critical point now. Basically here kissing this critical point. So if I increase this to 4,500, I'm now dealing with the near critical gas condensate that I'm dealing with right here. That's what's happening when I shoot up to this case 13 here, 5,000-6,000 GOR. This is probably 7,000, 13,000, 30,000. So this is a lean gas condensate, but we know it's a lean gas condensate because the GOR is increasing like this. Here we have another example of a lean gas condensate. This is probably, this is probably 30, 40,000 scuffs per barrel, and this is around 80,000 scuffs per barrel. And if you're dealing with a or a dry gas, the GOR will be 0. So for a dry gas, what we'll look at later when we're going to do the exercise is that we're going to use the dry gas method right here and just put the specific gravity to 0.6. When it comes to these different special cases, there are a couple of special cases that it's good for you to be aware of. Those, the first one is a saturated reservoir. A saturated reservoir is a reservoir where the initial reservoir pressure and temperature is already at the phase envelope right here. As soon as you go, you start to produce this well, you're already below the saturation pressure, and that's what's called the saturated reservoir. And the reason why this is complicated many times is that you're already inside of the two-phase party from day one. So your GORs are already starting to increase from day one. And what makes this really, really difficult is that, okay, if you're below the saturation pressure, GOR is not a function only of the initial producing GOR, but it's a function of relative mobilities. And that equation looks like this. This is producing GOR. These are some PVT properties. And this is rel perm terms right here. So this isn't as easy as when you have this clear, stabilized period of time where you're producing below the saturation pressure, or above the saturation pressure. Okay, so I just want to show an example of that in practice. If I had, let's say I had this well, it was like 750, or I can just make a new one. So if I have a case of 1,000 scuffs per barrel and I produce this, now I'm just running a numerical model, but you'll see the same thing. So, if I have a period of time here of 1,000 scuffs per barrel, then I hit the saturation pressure and my GOR is going up. Everybody sees that here. Well, then it's very easy for me to initialize the fluid with 1,000 scuffs per barrel. The problem is, okay, what if my saturation pressure was actually, let's say it was 3,200 at the GOR, and that's all. If the reservoir pressure, and I'm already here, and if I did this exact same run now, a little bit of my challenges is that, okay, the GOR is shooting up right away. Okay, is it 1,000? Is it another number? And here it might just because of this critical gas saturation. That's the challenges that we're dealing with in practice. And this is just a couple of cases where you see this. And in some basins, like Anadarko Basin, in the Montney, in other basins as well, we see these saturated reservoirs where GORs are increasing from day one. And in those cases, what you should do is that you can come up with an initial guess that the initial producing GOR is most likely around the early time period, but it can also be lower. So if you're dealing with a reservoir where you see this type of behavior, then most of the time your GOR is either the early time GOR or a GOR that's a little lower. And why can it be a little lower? It's because of this. Because if you have a free gas phase that's mobile, then your true producing GOR can be higher. It's the same thing here. In the example we ran, just after a few days here, you're like at 2,000, and it can be really tricky to work with those wells in practice. Another case that we see often is if you have constant GORs, but this is like, okay, the fluid type so low GOR that it can't be a wet gas. It must have a bubble point or a dew point, but the GOR is just flat, and it's like flat for a very long time, even when you go below the saturation pressure. And there's multiple explanations to this. One of the explanations is that, okay, your saturation pressure is just wrong. It should be lower, and that your bottom pressure is actually still above the saturation pressure. And that's a lot of cases where we've seen this in practice, that for some reason, some of the legacy wells are not able to draw down their bottom pressure low enough. Another example is that there's a huge pressure drop between the matrix and the wellbore. So if there's like a lot of damage or skin, or if there's a low fracture conductivity, or a lot of pressure dependent permeability in the fractures, for instance, then you can also predict exactly this type of behavior. And the last thing would be if you're dealing with like a dual kind of PVT system, where you have one layer with oil and another of gas. Then, okay, what you're seeing at the wellhead could be 5,000 scuffs per barrel, but in practice, you're actually dealing with, let's say, a very low GOR oil layer and a dry gas, for instance, and the mix of those two might look like a gas condensate, but it's actually neither of those in the reservoir. And those are different ways you can easily model it. What's actually true for your reservoir, that will be a little bit of a function of what reservoir you're dealing with, and also there can be multiple hypotheses of what's actually correct for your particular case. Another special case you should be on the look for is a solution gas drive reservoir. Here we see a few examples of solution gas drive reservoirs. This is the first one over here. This is the second one right there. And how do you kind of recognize that it's a solution gas drive reservoir? Well, what you see is this little dip in GOR before it starts to increase. Same goes here, and that's also what we saw in the model when we ran the model. But if you typically, most of us that done reservoir engineering in school, we've been reminded, at least back then in reservoir engineering 101, what is solution gas drive. And solution gas drive, that is typically something that happens over a few idealized stages of production. And in chronological order, these stages are typically that you have production while you're undersaturated. So in this case, you have undersaturated production right here. And then when the production is, when you're saturated, but the free gas is immobile. And what is dictating that free gas? Well, if you have that free gas phase that's not mobile, that means that you have a pretty high critical gas saturation. Okay, and a critical gas saturation that's this rel-perm term right here. So if I took this case, I can just show it one more time here, 8,000, and then you just run maybe a sensitivity or something like this on this SG term, and I'll show you how that looks like for 0.00, 0.05, 0.1, 0.5, and then 0.2. So that critical gas saturation term is just what will, okay, the larger that critical saturation is, just the more gas needs to come out of solution before that gas becomes mobile. So this dip here, the higher that critical gas saturation is, the longer that dip would be. So if we went in and looked at these different GORs right here, they would dip further down the larger those values would be. The last part is just, okay, when you have gone through or below the critical gas saturation at self, and the free gas is mobile, then that's when you see that GOR is increasing. So that those are pretty common to see in a few basins. You see it a lot in the powder and DJ for some reason. But if you see that in practice, that's this dip here would be related to number 2. A very special case is decreasing GORs. I have to be honest, decreasing GORs is something I see very seldom, but if you see that in your asset, then at least the only way I know how to model decreasing GORs is with a dual PVT system, where you have a higher GOR gas layer that depletes first, where you have lower viscosity, and then a lower GOR layer that depletes later. So that has higher viscosity. And that's the only way, at least I've been able to model it. But if you have a case like that, let me know. It'll be interesting to work on it, but very seldom to see it, at least my day-to-day work. The absolute last thing, I think, just on GOR trends in general, is 2 special cases. So we have 2 different GOR trends that we're looking at here. The case to the left would be a case where you hit the saturation pressure and your GOR shoots up to kind of like a new plateau. And the other one is, okay, I go below the saturation pressure and my GOR increases almost linearly. And typically, what we see to the left here, when it shoots up, there's a very little pressure drop between the matrix and the wellbore. So there's no skin, no damage, no low fracture conductivity, etc. In the case to the right, we're typically dealing with some kind of pressure drop between the matrix and the wellbore. Is it skin? Is it damage? Is it low fracture conductivity? High pressure dependent permeability in the fracture? Varying conductivity throughout the fracture, etc. Could be a little bit hard to say in general, but that's if that's something you see in your data set, at least a very effective way of modeling that is just to lower your fracture conductivity to a lower number. Okay, so hopefully that has given your eyes at least a little bit of different cases if you see some of those cases in your day-to-day work, you know ish how you can initialize them. And we also will go through a few wells that will initialize together in the exercises now coming soon. Before we do that, we want to cover very briefly some items related to petroleum fluids. When it comes to petroleum fluids in general, what we would like to know. We're just going to talk very briefly about fluid sampling, and then we're going to go through like a PVT report 101. And then we're going to end the day today talking about PVT models and go through a few different exercises on the PVT model side. Very basic on the petroleum fluid side, as we are dealing with call it 3 different families of petroleum fluids. It's alkynes, it's naphthanes, and it's aromatics. And when we go into a new field and we would like to quantify, what's kind of unique with this particular field, we try to quantify is the, from a scale from being very paraffinic to very aromatic, what we call relative paraffinicity or aromaticity. Where are we in the world? Where is Permian versus the Eagle Ford versus Montney, etc. And to do this, we calculate a number that's called the Watson's characterization factor. And that takes in 2 inputs, the molecular weight and the specific gravity, and it gives you this very nice index from 8.5 to 13.5. And then numbers in the 12.5 to 13.5 range, that's typically naphthenic compounds. And in the 11 to 12.5, then you're dealing with aromats. And when you're 11 to 12.5, that's naphthenic compounds, and aromats are 8.5 to 11. And of course, there will be some overlap in some of these components. So when we've worked with a lot of you guys and we created these different equation of state models in the different fields, we have created this plot right here, which is a specific gravity versus molecular weight plot. And increasing paraffinicity is essentially going down here. And what we see many times is that each of these different fields, they follow a very specific trend, and either they're very paraffinic or they're very aromatic or there's something in between, which is what we call naphtha. When it comes to the compounds themselves, typically you will deal with a lot of non-hydrocarbons in addition to the hydrocarbons that we just talked about. The most common ones are CO2, H2S, and nitrogen. CO2 and H2S, they're always unwanted and costly to deal with, while the nitrogen is typically there to reduce your heating value and what you can sell. So those would in most cases be there in addition to the hydrocarbons. I'm also very confused many times between all the different abbreviations when it comes to NGLs, LPGs, LNGs, etc. So we also have a little slide just covering, okay, what is actually the difference? And if we look at LNGs, that's just the liquefied natural gas, so that's C1. LPGs are typically just C3 and C4. NGLs will be these components from C2 to C5. And crude oil will typically be components that's heavier than C5. And in your day-to-day life, like methane is used for heating, ethane for plastic, propane for heating, typically butane for heating. And then everything that's heavy and that you really put into your car, that's the components that's typically higher than C5 plus. And when you have these petroleum fluids in the reservoir and you would like to sample them, there's a few different types of samples that you can consider sampling. In shale reservoirs, it is typically a separator sample. But the reason in general why we sample is that we would like to have PVT data to develop a PVT model, an equation of state model, which we'll talk about in a second. If you wanted some general recommendations, just like very boilerplate general recommendations for sampling in general, call it the industry standard recommendations are on this slide. This is not for presentation, but more for reference. And it's to collect samples early in a well's lifetime at lower drawdowns and stabilized rates. So stabilized GORs essentially, and then try to report the following data right here. So if you come in early and as long as the rates are stabilized and you sample and most of the labs will report this data, you should be in good shape. But just remember here, this difference that we talked about earlier, where there's a difference between what's reservoir representative and in situ representative, that has nothing to do with whether the PVT data is accurate, okay? So just make sure that once you get a PVT report, even if that PVT report is not perfectly recombined at the right GOR, a very specific example would be like one of these examples we looked at here already, where the GOR Let's say I sampled here early and I made a GOR recombination in the laboratory at 12,000. Don't throw out that PVT report that you paid 30 grand for. It's still extremely valuable if the data is good. And if you just want a basic overview of the difference between the two, you have the slide there for reference. When it comes to sampling, we have 3 different types of sampling. The one that's very common is production tests sampling, and that's typically done for separated gas compositions, sometimes also for separated oil compositions as well, and stock tank API gravity. And it's used many times just for testing. A lot of it in Canada. We see it a lot of it also here in West Texas, and it can actually be used as an input to initialize a fluid in Whitson processing. So we have a method for that that's called separator compositions right here, that you can input this data and use it to estimate your composition as well. These are typically $500 to maybe $2,000 depending on what company you work with. They're very readily available, not necessarily super accurate in general. The separated sampling, that's the most typical sampling type we see when we've done these field-wide equation of state models for all these unconventional basins. Is that we have a separated gas sample, typically in a 20-liter container, and we have a separated oil composition as well, and then we recombine that physically in the lab. So that's a difference between production test sampling and separated sampling, is that with the separated sampling, we recombine the GORs in the laboratory at some kind of GOR that you pick. You as an engineer, you go and tell them, let's use 1200 versus 750 or what not. There's different techniques to QC that the sampling conditions are correct. Another alternative would be to use bottom hole sampling. That is not used that much in unconventionals. I've seen maybe 5 of several thousands of those reports being bottom hole samples. The bottom hole sampling, that's typically recommended when you're dealing with undersaturated oils. And the reason for that is that you need the sample to be single phase. So your flow bottom hole pressure needs to be higher than the saturation pressure. And it's in general not recommended for gas condensates and highly viscous oils, etc. Another thing that is more of a conventional option is an open formation testing tool. And that's just a way for you to take literally a direct compositional sample at a point space. You have like, okay, at this particular point, this is really the composition. And very important for offshore reservoirs, but not, I've at least never seen it being used onshore because of the low permeability reservoirs that we're dealing with there. But that's at least a option in general if you're dealing with offshore reservoirs. I know some of you guys also have offshore assets in the company. Before we're going to go into the PVT models themselves, we need to learn a couple of things about PVT reports. And what we're going to do is going to go through kind of a crash course on a PVT report. How does a PVT report look like? What lab experiments is in a PVT report? What data in the PVT report is actually measured versus calculated. And we're going to talk about compositions, and we're going to talk about a special thing related to API gravity. And we also going to just emphasize that we don't put PVT reports into a simulator. We always have to go through a model, whether that's a correlation or an equation of state or something else. So the first thing that we would like to just acknowledge is like, okay, how does a PVT report actually look like? And here we have an example of this is one from Canada. In Canada, a lot of the PVT reports are public. If you've never seen a PVT report before, it has hundreds and hundreds of pages. And I'll see if I can pull up one just here. So here you see an example of the PVT reports, and they typically have literally hundreds and hundreds of pages sometimes, and tables and figures and everything. So many times, if you just want to, like Adam Smith asked about formation volume factor, finding a formation volume factor in a PVT report could, in many cases, be like finding the needle in the haystack. It really can be sometimes, and it's because you have different types of formation volume factors being reported. Some of them are adjusted for separated conditions, some are not. Some of them have a single stage process associated with them. Some of them have a multi-stage, etc., etc., etc. So they're extremely call it complicated, and they have a lot of data that's calculated and some that's measured. So that's kind of point number one. The different types of experiments that we typically find in lab reports is compositional experiments, standard PVT experiments, and gas EOR experiments. And in this one slide, I'm just going to teach you, okay, of each of these different experiments, this is what we actually measure. So if we start with the compositional, typically we use something called the GC, and the GC measured the weight percentage of the individual components. This is what's being used 99.999% of the time. But since we need actually the mole amounts in the model, we have to assume what you call molecular weights to do that conversion. If you have a little bit more money and if you have more time, some people like to get the true boiling point distillation experiment as well. That gives you the weights, the molecular weights, and the specific gravity. The CCE experiment is what gives you the saturation pressure. The depletion tests, like DLE and CVD, gives you the liquid relative volume. The multi-stage separated test, that is what gives you the formation volume factor that was asked about earlier. The viscosity experiment gives you the oil viscosity. Very important there. We never measure gas viscosities. Because why don't we measure gas viscosities? Well, the main reason for that is that gases, they're typically primarily made of very known hydrocarbons. So it's very, very easy to correlate what the gas viscosities are. If you are in the world of gas EOR, slim tube experiment gives you the multi-contact MMP pressure. Swelling test gives you the first contact MMP pressure. And the multi-contact vaporization experiment gives you the vaporization efficiency. And that's it. That's basically almost all the PVT experiments that at least I interface with on a day-to-day basis. And I'm sure you all as well. When it comes to the accuracy of these different types of measurements, we've added a couple of slides just so you have that for reference, what typical accuracies of these different experiments are. So there's 2 slides there that you can just use for reference. But just remember that the biggest uncertainty of all the measurements are typically the oil viscosities due to calibration. That typically is 10 to 20% plus minus. And in addition, that's also the hardest thing to model. So that's what we talk about here. That's the last part. The third part that I just wanted to convey to you all is the amount of data in these reports that's actually measured versus what is actually being calculated in general. Here we're looking at a reservoir fluid study. And that's the compositions that we provided in the PVT report, the compositional analysis of a reservoir fluid. And here we see all the different components, component names, the mole fraction, and the mass fraction. That's what we're looking at right here. And if I asked you what of this data is actually measured, so this is the reservoir fluid composition that you've sent to the laboratory, and I'd like you to just spend 15 seconds, think about, okay, what in this PVT report right here on this page, what is actually being measured versus what is actually being calculated. So of course, it's kind of like a trick question because nothing here is measured. So this is the reservoir fluid composition. You have both the mole fraction and the mass fraction, and neither of those are directly measured. Okay, so maybe some of you will think, well, isn't that the most important thing in the whole report? Well, definitely is one of the most important things or that you would like measured. But the truth is that they're not measured directly because some people think that you can just take a reservoir fluid into a PVT cell and magically we measure the composition of that fluid magically. Just like, okay, there's a measurement device that just magically measures the total composition of what's in that cup. And what actually happens in general is that you recombine the separated fluids. So you measure the composition of each of those separated fluids individually, and then you physically recombine them. But to get the composition of the separated gas, this one you put straight into a GC, but this guy, an oil, you can't put straight into a GC. So that needs to be flashed to stock tank conditions. You need to measure this individually, then you need to measure this individually. You need to recombine them, then it becomes the separator liquid. Then you take the separated liquid and the separated gas, you recombine them together and mathematically, and you get a estimate of what you have in PVT cell, which is the reservoir fluid composition. And many of the labs, to QC what this composition is, they flash that with a single stage flash and get a new composition measurement of each of these. And you take those and you do just a mathematical recombination on a piece of Excel, like an Excel type of calculation, to double check what are actually this reservoir fluid composition is in reality. And most of the time, you get different answers when you do it this way and this way. And the accuracy is within 1 to 2 mole percent of methane. So pretty big discrepancy there. And the formula for that, when you do a mathematical recombination, is just this formula right here. But again, this part right here, this composition right here in green, which we saw on the previous slide, it's not measured directly. You're basically measuring, it's 1, 2, 3 different compositions, and then you're doing a mathematical recombination, or you're doing a single stage flash on the back end, and you're doing a mathematical recombination of those. So there's no magical way to just put in a reservoir fluid composition into a PVT set. Okay. And when you measure these compositions, that's what we talked about earlier. We can measure the non-hydrocarbons. We can also measure the compounds with known molecular weights. That will be everything up to C6. Then we can have some isomers, for instance, benzene and toluene. But when the carbon numbers become high enough, like C10, C11, and C12, what happens there is that we have to report them as single carbon numbers. So that's not like a component, but it's actually a mixture of a lot of different components. So C14 or C15 can have like almost 2,000 isomers making up those components. But that's impractical to actually measure in the laboratory. So that's why they talk about these single carbon numbers when they report a PVT report like this. And just for reference, if any of you have worked with oil-based muds, the oil-based muds, they typically have components from C12 to C20. And the reason why these compositions are probably the most uncertain thing that you measure in the laboratory is not only because there's so many stages that we talked about, but it's also the fact that when you run a GC, you're measuring not the moles that you like to use, but you're measuring the mass, and you're measuring the mass fraction of each individual component with the GC. And you take these weight fractions and you convert them to moles by using the total molecular weight and the individual component molecular weight, which is this formula right here. This number you measure from the GC. This one you can measure with a benzene freezing point depression method. And then this guy right here, this molecular weight is known for pure compounds. It's estimated for single carbon numbers, and then it's unknown for the heaviest component. So you can see how both the uncertainty in the measurement and the recombinations combined with this introduces some uncertainty within plus minus 2% of methane to these compositional measurements that we're making in the laboratory. Yeah. Second to last thing, I'll just a little warning, especially for our Canadian friends and also people here in the US. If you ever see these hydrocarbon liquid analyses right here, they are basically hydrocarbon liquid analysis at the separated conditions. They're not at stock tank, but many times they report these numbers as API gravity numbers. Okay. They report these as API gravity number, but an API gravity number, that should always be at stock tank conditions. And what happens with a fluid from separated to stock tank is that it releases gas, and that released gas is now included in the liquid API gravity calculation. So you get these ridiculously high API numbers. So these are not true. Be very aware of that, especially in Canada, because you should never use this to initialize your PVT, this number right here. My last point when it comes to PVT reports is that you never put them into a simulator. We need to build a model to replicate that data and put that model into into a software or whatever else to run the calculations. And that's the last part of the course that we're going to talk about today, which is this topic about PVT models. And there's two different types of PVT models that we're dealing with in the petroleum domain. The two models that we're going to deal with in this course is the compositional model, what we call an equation of state model, and it's also a black oil PVT model. Equation of state model, just on a very high level overview. If you want to understand how it's been developed, we like to go back to a kind of like a tank model, where if we look at a little particle and that particle has or exhibits some kind of pressure on the wall of this tank, we say that force divided by the area, that's what we define as pressure. If we have 4 different balls running around in the tank right here, this is kind of our base case. But if we increase the speed of them, which is analogous to increasing the temperature, we hit the wall more often. So we can say that the pressure goes up. If we increase the number of molecules, well, we hit the wall more often. Again, pressure goes up. But if we increase the wall's volume, it will take longer before these molecules to hit the wall. So when we increase the volume, the pressure will go down. And these were the different observations that was made, 200 years ago, that pressure is proportional to temperature, pressure is proportional to the number of moles, and pressure is inversely proportional to the volume itself. And that resulted in the ideal gas law, which was one of the absolute first equations of state that was introduced back 200 years ago. And then we got a little bit more advanced version of that, which we call the van der Waals equation. And the van der Waals equation, that is what we call a cubic equation of state. And in the 70s, we had a few different communities in the oil and gas domain that developed the so-called SRK equation of state and the so-called Peng-Robinson equation of state. And both of those equations of state are the industry standard today. They're both cubic, and they're used in 99.9% of the US calculations are either of these equations. Which one of them are best? Well, I'd say, and I think there's a lot of support, that neither of them are better than another. And I think you can even take one and convert it consistently to another. The reason why we have 2 is because the SRK equation of state became really popular in the facility and processing community, while the Peng-Robinson equation of state became really popular in the reservoir community. So that's why we have 2 in general. We talked already about what an equation of state model is. It requires 3 inputs: temperature, pressure, and composition. And with that, we can predict the different types of PVT properties. If I asked one of you guys to send me an equation of state, you would basically send me either of these equations, and that will be represented by 2 tables. And those 2 tables, they will be kind of defined for that particular reservoir or that particular basin. And that's what we've done with all of these unconventional basins in North America. We've taken PVT reports from all these different locations, from all the different laboratories. We've made one equation of state model for each of those basins, such that you can go out to every well location and initialize PVT on a well-by-well basis. This is what we call a multi-sample equation of state model, which just means that what's unique from one well to another is the composition, but the equation of state itself and that composition is everything that's required to predict PVT data for that specific fluid. And then a very natural question from you guys would be, okay, why can't we just use one equation of state for every single well in the world? Well, that's a great question. The reason for that is that all these components that are heavier than C7, they will be different from basin to basin. And that comes back to, if we took this example with C14, C14 is actually up to 2,000 different isomers. And what your job is in one basin is to kind of find the average C14. And the average C14 will be really dependent on whether that fluid is paraffinic or aromatic or something in between, which we call naphthalenic. Okay, so most of these different plays, they will have a, so if you go to our webpage, for instance, here, and we look at like the Permian, for instance, all of these different plays will have different set of equation state tables. And what equation state is being used for your particular calculation, you can see here to the right. This is just a default Peng-Robinson equation state, where all of these components right here, if I zoom in, nitrogen up to C6, they are the same whether I go to the Gavar field in Saudi Arabia, if I go down to Vaca Muerta, if I stay in the Permian, if I go up to Montney. But what happens is these components that are, C14, for instance, will be very basin specific. That's why you need to have different characterizations when it comes to the fluids in the different basins. So with that, we're going to take the last little break, and then I see there's some question right here as well. I'll do the question from Sheriff here first. So what is a typical increase in producing gas oil ratio relative to the initial RS for solution gas drive reservoirs? Is a doubling a fair estimate? That is a very good question. and I think there's not a good answer to it. There will be good rules of thumb in different basins, but like we've seen wells in the Anadarko Basin that starts up at 1,000 scuds per barrel, and after 3 years they're producing at 300,000 scuds per barrel. So I mean that's a 300x multiplier. There will be very basin specific probably rule of thumbs there, but not in general. And I'm sure there's maybe something else there going on. Maybe there's another gas layer or something like this. But very, very hard is something to generate some general rules of thumb on that item. Perfect. We'll take 10 minutes. We'll be back here at around 11 Houston time. Perfect. See you in 8.
Yes, there's another question added. Can the GOR decrease in the very late stages of reservoir life?
Yeah, it can. The best and in short, like it's very easy to model something like that, Sheriff. And it's a good example is if you have like an SRV, you've drained the whole SRV, it's not very productive anymore, and it's the non-stimulated part that starts to feed in and dominate the production. While that solution GOR of that unstimulated rock will be higher than the depleted area, so the GOR will start to go down. And I think the best guy to talk about that is Steve Jones. He has a GOR paper with basically here. This is a good example where you have a well, it's infinite acting, hits saturation pressure, goes up to another plateau, increases in boundary dominated flow, and then you have this unstimulated rock that starts to, after you deplete the whole stimulated rock volume, you have that entering the system and your GOR goes down. And we've seen that in some cases as well. Another example is if you have a very aggressive kind of artificial lift, you've been on ESP or something like this, and then you go over to rod pump and you're not able to draw down the well as much as you did before. So your bottom pressures are lifted up. That's more of an operational thing, but that will lift your decrease your GORs again. But yeah, excellent. So we'll go ahead and start a few of the exercises. As I mentioned, there won't be that many exercises for this course compared to a lot of the other courses, but we will go ahead and do the exercises in this one short one now, and then a little bit longer one in the end. The first one we're going to do is just to use an equation of state to predict compositions. That's the first thing we're going to do. And the reason why we would like to predict compositions is because temperature and pressure, we can get good estimates of that throughout the basin, but a composition can be hard for us to find good estimates of that. So we need to have different methods for us to predict the composition based on GOR or whatever else. And when we have that, we can predict the PVT properties. So if you wanted to get the composition, the way you would do it if you went to a lab, you would pay $10,000 for sampling, $40,000 for lab analysis, and then they'll try to convince you to store the sample there for $20,000 a year. And then I'll send you a PVT report with 100 pages, and you want to find a composition to use there. Well, kind of a needle in a haystack job. So what we try to do is to allow you to use all the data you have to create an equation of state model, and then we go out and use that equation of state model for all the wells where you don't have PVT information. And that's what we're going to do now in a very simple exercise. So I'd like you to open up Whitson Plus and just make sure that you're in your project. So if you click wells here to the left, you'll be in your project in Whitson Plus up here. And this first one is going to be pretty basic. The first thing we're going to do is we're going to create a well. And the way to create a well is just to click add well up here. That's how we add a synthetic well. And we're just going to click, we can just call it test or something like this. Doesn't really matter what we call it. And when we have the test well, it should look something like this on your screen. So let me know if you haven't gotten there now. It automatically should pop you to the PVT part. And the first thing we're going to do, we're going to just create a very simple fluid. We're going to make a 10,000 scuds per barrel fluid. To do that, we just open up the card here and we put in 10,000 and we click save. We'll show that one more time. We open up the reservoir fluid composition card. We make it 10,000 here. That's 100 barrels per million. Generates this phase envelope, and we can go to the PVT table and we can check. Okay, what type of fluid is this? Is this a gas condensate or is it something else? And of course, this is a gas condensate with a dew point of 5 or 6. Okay. And this is the phase envelope. Then we're going to change the GOR to be 600 and then the API to be 38. That's another method. So we're going to open up this reservoir fluid composition card again. We're going to change it to API and GOR, and we're going to make that 38, and we're going to keep this other guy at 600. I'm going to click save. That's going to change our phase envelope to something very different. Now we're to the left of the critical point. We're dealing with black oil, and we could go to the PVT table and we see that we're dealing with the black oil with now a bubble point. Same equation of state in the background, just a different composition. How do we know what the composition that's predicted has been? Well, we see that here. We can click this I symbol right there. That's on the fluid composition card. Then we have a method called GOR and saturation pressure. And for this method, we are going to use 1250, and we're going to use 3000 as our input. So that's this method right here called GOR and saturation pressure. And the saturation pressure, that's what we wanted to make. Was it 3000? And then we were going to make the GOR 1250. We'll click save now. What we've basically done is that we've constrained it with 2 parameters. We want to have a GOR that's 1250, and we have a bubble point of 3000. And sometimes that might be required because, let's say you want a composition in this basin with this equation of state that hits the saturation pressure at a certain pressure. And the reason why that's relevant is because, if your bottom hole pressure goes down and then exactly when your bottom hole pressure hits 3000, you see that the GOR shoots up. Well, then most likely that's your saturation pressure. So that's a way for you to kind of initialize your wells with the GOR and P set. The absolute last example would be to create a dry gas. And to do that in reservoir fluid composition card, we open this guy, we change the method to dry gas, and that could be either a composition or it can be a simplified input. We're going to use the simplified input right here. I'm going to make the specific gravity 0.6. Then we're going to click save. And what you'll see now is that the phase envelope is extremely boring because there's no two-phase region. Well, it's so dry that there's no two-phase region, but it still will predict to a composition, and it will still give you a PVT table. But the PVT table will be extremely boring. Okay, so that was the first little exercise just to get us warmed up a little bit. And then we're going to end also up with an exercise a little bit later. So now we have an equation of state. We know that we can use the equation of state with readily available data to predict the composition. And once we have predicted the composition, we can use the composition and the equation of state to create a black oil PVT table. And again, if you want to know what the black oil PVT model is, well, you think about an equation of state. An equation of state has pressure, temperature, and composition as input. We think about the space there. The solution space is huge. It's 2, which is for pressure and temperature, and then n minus 1 dimensions, where n is the number of components. It's like none of us can think in that space. Maybe some of us can do 3D. I'm more of a 1D guy, but maybe some of you guys are smarter and can do 3-dimensional chess. But the nice thing with the black oil model is we go and we simplify our world. We say, well, what if it was just 2 components? And that's the surface gas component and the surface oil component. Well, then we're dealing with the so-called black oil model. And here is important to remember that the black oil model can be used for all reservoir fluid systems and not only for black oils. So why do we call it a black oil model? Well, it's just a tradition. And it comes from the fact that, when we introduced the model, it was a 2-component PVT model. But back in the days, there was no condensates and stuff like this. We hadn't gone that deep. So when it was introduced, it was just oil, and that oil in the tank that was always black, and then the other component was surface gas. But if thinking back at it, we should probably have called it the 2-component PVT model. But here we are. Everybody knows it as the black oil PVT model. It has 2 components, and it has 3 parameters for each component. And then the way you kind of deal with the composition, how much is of each phase, that would be to adjust the solution GOR or the RV curve. And as we talked about before, it is process dependent. And if you want to go in and actually define these different terms, these different model parameters right here, formation volume factor, RS, and viscosity, to do that rigorously, we need to introduce some vocabulary from SBE. And if we look at an oil reservoir, we talk about VO as reservoir oil. Then we talk about anything that originates from that reservoir oil that at surface would end with, so VO hat O is surface oil originating from reservoir oil. VG hat O is surface gas originating from reservoir oil. And vice versa on the gas side, if you have a gas reservoir, okay, you can have surface oil originating from the reservoir gas phase. That's what we call condensate. We can also have surface gas originating from reservoir gas. That's what we call that's just gas at surface. So you can have both oil and gas at surface that originates from either the gas phase or the oil phase in the reservoir, and that's why you need to define and introduce these symbols right here, which SB did in the phase behavior monograph written by Curtis. So if we look at this, if this is our reservoir, we have a free gas phase, we have a free oil phase. So if we look at the gas phase first, and we get these different components depending on where they're coming from. We know that the formation volume factor for gas is Vg divided by Vg hat G. So that's the volume at surface originating from the reservoir gas phase. And then the RV term is the surface condensate originating from that reservoir or divided by that surface volume of gas. On the formation volume factor side, it's the reservoir volume of oil divided by the surface volume of oil originating from that oil phase. And then RS, that will just be the solution GOR, so the surface volume of gas originating from the reservoir oil phase, and then divided by the surface volume of oil originating from that oil phase. And these components right here in the Blackwell PVT model, and the Blackwell PVT model, again, that's all these parameters right here that will be generated on this page that you can export into any third-party tool. They are process dependent, while viscosity does not care about the process. Okay, so again, if I did this exercise we did earlier, where I basically had a composition, let's say I had a composition right here, and if I keep the composition the same here, you see the viscosity and the bubble points, they will not change, but these properties right here, formation volume factor and GOR, they will change. So if I remove these, you'll see these parameters were the same, these were increasing right here, okay? And that's what we mean by these being process dependent, these guys right here being process independent. And if you want a quick overview of the formation volume factor, this is how it behaves above the bubble point. It hits the bubble point, and then it starts to decrease in the saturated period or a region where it releases gas. And the undersaturated part, that's so basically any point above the bubble point, the solution GOR is constant, and then it goes down as you go below the saturation pressure. The gas formation volume factor is very hard to plot graphically, so that's why in Whitson plots we typically and what is typically recommended is to plot the inverse, which is the gas expansion factor. So that's what you'll see here being plotted. It's just easier to read. If you were like over here, it's easier to read it graphically. And that's just the inverse of the gas formation volume factor. And here's the dew point. The solution OGR is constant above the dew point, and then it decreases non-monotonically below the dew point. And to understand that and why that happens, we just need to talk again about K values. And K values, that's again this concept of which of these components like to be in the gas phase versus the oil phase. We mentioned that already once. So if my relative preference is to be in the gas phase, my K value is higher than 1. If it's below 1, it's a K value below, or it means that I like to be in the oil phase. Why is the K value behaving as it does? Well, that will be the same as it's like a physical property. So it will be the same as asking, why does water boil at 100 degrees C? Well, it's just a physical property of water. And if you look at these K values, they tend to be decreasing linearly on this like or on this log plot right here at low pressures. And then it's this region where they start to turn non-monotonic, at least the ones of the heavier sort. and they end up at what we call the convergence pressure. And this region right here can be really dependent on fluid type, temperature, and pressure, etc. So this is a very complex thing to model that is only really dealt with rigorously when you have an equation of state. And this is what we call the shape of the nose, and it's very relevant at reservoir conditions. And I know your brain is hurting now, but just bear with me, because these retrograde condensation, why you see this concept right here in the laboratory, why you see this concept right here when you are dealing with a solution CGR, that you have a condensation-driven period and then a vaporization-driven period, it's because of these K values. It's because of how they behave. And the K values of these heavier components, they go down and then they start to go up. So it turns from this net condensation-driven period to this net vaporization-driven, not period, but like range of pressures. So that's why you see this shape if you did this in the laboratory, or in Whitson Plus, why this thing goes up in the end. So a lot of people come to me and it's like, is this right? It doesn't look right. It goes up. And it's like, well, it's actually a very physical process that is true, and that you can measure in the laboratory. Very good. Now we're going to do a very quick thing. We're not going to do an exercise there. I'm just going to explain it. But maybe to Adam Smith and all the folks that are running type of PVT calculations for a wide range of fluids in a basin where you maybe span oil, gas condensates, and all the other things in between, it can be really helpful to know. So this is a little trick. If we're dealing with an oil reservoir, the formula to calculate oil in place is very easy. It's hydrocarbons in place divided by the formation volume factor. So it's this formula right here. If you want to get the gas in place, we just take the oil in place and multiply it with our RS, right? So if you go here, oil in place will be hydrocarbons in place divided by this number, and then you would take whatever that result is and multiply with this number. That's your gas in place. Then your gas reservoir, to be able to find your gas in place, what you will learn in school is that you would go in and take the hydrocarbon pore volume and divide it by the formation volume factor, and then you would take whatever that gas in place is and multiply that with the RV term. But today I'm going to show you another hack, which is really helpful, and it just makes your life very easy when you go through these mapping exercises. And it's just to treat or use two equations, just two equations for every single fluid system. And that's these equations right here. So it's basically to use this concept that was introduced by SB called total formation volume factor. The total formation volume factor, that is a number that can be calculated for all fluid systems. It's calculated and reported automatically in Whitson Plus. The same goes for GOR. How it's defined, it's defined as such. It looks a little bit complicated, but what you can see is if you have 100% oil, this will simplify to BO. And if it's 100% gas, it will simplify to BG over little RS. And if it's anything in between, you have two phases, for instance, it will just be a saturation weighted average of the two. For a total GOR, it's the same thing. Okay, if you have 100% gas, then your GOR is equal to RS. And if it's 100%, or if it's 100% oil, it will simplify to RS. And if it's 100% gas, it will simplify to 1 over RS. Okay. And where this is being reported, so you see here in Whitson Plus, the total formation volume factor, and the BO is the same for an oil. Where it becomes different is if I went in and made this a gas condensate, then the total GOR will be 10,000, and my total formation volume factor will be this number right here. And I could then go ahead and apply these equations right here for every single well location. So you get these beautiful continuous oil in place and gas in place maps that you can use no matter what the fluid is. So you don't have to, like, on every well, okay, is this an oil or a gas, and then use a bunch of different equations for that. You just apply the same formulas and it becomes comes out really, really nicely. So that's a little hack. So just to show you a quick example of this, let's say your hydrocarbon pore volume is 5 million reservoir barrels. And I have three different scenarios here, I have an oil reservoir, I have a gas reservoir, and a two-phase reservoir. Okay, if I wanted to calculate the oil in place for this oil reservoir right here, I take 5,000 and I divide that by 1.93. That gives me my oil in place. That is around 2.5 million barrels. and then I multiply that number by 2000, and that gives me 5.2 BCF. And I can simply use the same formula. 5.9 is my formation volume factor. So if I take 5 divided by 5.9, I get 846, and then I can take 846 and multiply with 10,000, I get 8.46 BCF. And if it's a two-phase reservoir, which is very common in the Montney and in the Scoop Stack as well, you can take the number right here, 2.46, and take 5,000 divided by that gives me 2,000, and I multiply 2,000 with 2,000, that gives me 4 BCF, right? So the same equation, but 3 different reservoir fluid types, and it just makes your life easier instead of having to like go in and define every single different fluid inputs. We're going to jump very soon into the last piece of the course today, but we're just going to talk very quickly about black oil table generation. And the reason for that is that black oil tables, even if you have an equation of state, that is the working horse of the oil and gas industry. Whether you like it or not, most likely there's a black oil table that's being used behind the scenes when you do at least any pipe flow calculations, any type of numerical simulation, etc., etc. When you generate a black oil table, you do that with an assumption of a constant temperature. That works great in the reservoir, at least for depletion purposes, but in the pipe, you need several PVT tables there to span a wide range of different temperatures. But as we mentioned before, the black oil PVT model has 3 different components related to it. It's RS, it's formation volume factor, and it's the viscosity. And on the gas side, it's the same thing. It's essentially a term that decides the ratio. It's how you take whatever that fluid is and converts it to what the volume it is in the reservoir. And then it's a term that basically says what is the viscosity at those conditions. And then the only parameter here is the pressure that is changing. And that is something that's used as an input to reservoir simulation, RTA, PTA, pipe flow process, etc., etc., etc. It's extremely fundamental. To create one, well, you just need 4 different things. You need an equation of state, you need an assumption of temperature, you need the composition and the surface process. These are all inputs when you, and we designed it like that. So when you input this, software is predicting a composition. That's automatically creating a PVT table that you can generate to any third-party tool if you want to. And of course, here we have a temperature, we have a composition, and behind the scenes, we have an equation of state. So that's the inputs that is really needed to create any of these formation volume factors. And again, these if we look at what the inputs are to a black oil table generation, we just covered that piece. The components are oil and gas, and there's 3 properties defined for each component. One assumption that's being made is that basically the density of what is condensate from the oil phase and the gas phase at surface, and the same on the gas side, that they are the same. And it's a pretty decent assumption, but obviously in practice, that's not true. You also, as we mentioned 2 times before, you'll see that the PVT properties are process dependent, so they will change depending on what your assumption of surface process is. And in general, a reservoir temperature, as I mentioned, that's assumed to be constant. Back in the 80s, we usually dealt with these black oil tables. That was what we call traditional black oil tables. They were missing the RV term right here. So when you're asked to use a black oil versus a liquid rich table, you're basically, okay, the black oil is probably ignoring the RV term that should be here. So never use this, in Whitson Plus we don't even allow you to not use this. But in the 80s, we got introduced this modified black oil table. It's what you're looking at right here. It has this RV term or this RS term, and it accounts for the condensate that's in solution with the reservoir gas phase right there. And a black oil table in general will not only have properties for these curves right here, but it will actually have properties for every single undersaturated curve as well that you're looking at here as an example. The other thing that you could do, you could also extrapolate those tables to what's called a critical point, such that they'll become kind of 100% continuous across the critical point. That's what we call an extrapolated black oil table. And a lot of the softwares now, they do that automatically. We talked about reservoir fluid classification earlier today, but if you want to have some rule of thumbs here when it comes to BO and RS, so this is basically these terms we talked about earlier, the total formation volume factor and the total GOR. Well, we have some rules of thumb also here for different types of fluids. So, you know, if you're dealing with a black oil, volatile oil, critical fluid, etc. And here, you know, the question we get a lot is like, you know, is this basically saying you have a formation volume factor for a gas condensate? Well, you can calculate an equivalent of it, yes, and it will be a much higher number, obviously, because the oil will shrink much more. The leaner that fluid is, and this is just a total GOR in general. So that's another rule of thumb table that we have provided, and that's being referenced a lot in general. Just a reminder here that every single black oil table can be used for all reservoir fluid systems, not only for black oil systems. And my absolute last thing that I wanted to just talk to you guys about was this the reservoir water in general. Okay. How does it actually impact our analysis? Why does it impact our analysis, and when does it impact our analysis? How do you, first of all, change it in the software? I think that's the first thing I want to cover. Multiple places where you can change it. One place is here in fluid installation in the numerical model. You can also change it in numerical RTA, and you can also change it in the bottom hole pressure feature as well. What you see here is that salinity is one of the inputs. So if I change the salinity, you see that my density and viscosity is increasing. And typically salinity ranges from 0, which is fresh water, all the way up to 300 parts per million, or 300,000 parts per million. And you see from 100,000, if I made that number 3 instead, you see that the density is changing a lot and the viscosity is more than doubling. So it starts to become really important when you have really, really saline formation water in general. And it will primarily have an impact on viscosity and density, where probably the biggest day-to-day impact, honestly, for most of you guys would be if you have wells that produce a lot of water, it will tend to have a big impact on your bottom hole pressure calculations in general. And that's just why we included this slide in general. But water viscosity, they typically range from 0.3 centipoise up to a centipoise. Compressibility is fairly constant, not very compressible, and there's essentially no shrinkage. In some edge cases, there could be some gas in solution with the water, but most of the times you won't really care about that volume. Perfect. The last thing we're going to do today is to go through the exercises, and that's the only thing we're going to do before we're going to take lunch. And we're going to do a oil well, we're going to do a gas well, we're going to look at a few different ways of initializing fluids. We're going to generate a virtual PVT study, and maybe a few other things. So to get started with that, we'd like everybody just to go back to their project. Just click wells here. Make sure that it says your project here at the top. Yeah, just do your project there at the top. And then we are going to go through these exercises, and I'm going to just do those on my side right there. We're going to start with the first well, which we call the kite well. You're going to open the kite well and go to PVT right here. And the first thing that we're going to do is to try to come up with an estimate of the initial producing GOR. And the way to come up with an estimate of that would be to either write in a number here or drag and drop this line. In my opinion, if this was my well, I would ignore this early time data right here, and I would go in and pick a GOR of 750. That's probably what I would pick. And then click save. Once you've done that, if you want to look at your composition, you can view the composition right here, and you can copy that composition into Excel. So if you copy it here and I open up Excel, for instance, it should just be a simple pasting in right here. What we see here is that we don't have any non-hydrocarbons. If you actually had one of the studies that we have, if you did the exact same method, you will kind of get basin-wide averages there. But you can also set these non-hydrocarbons to be something that is not 0. So that's the next thing that we're going to do together right here. We're going to go in and we're going to open the reservoir fluid composition card. We're going to say set non-hydrocarbons. And here we're going to write in 0.5, 0.7, and 0 as our inputs. Okay. And when we're done with that, we're going to just click save. Now the composition is being run again. And if you open up this, you might have to just refresh one time there with that happen. That was a little bug we fixed the other day. Then you'll see that your nitrogen CO2 shows up shows up here. If you want to check what the saturation pressure is, one way is to you can of course go here and go into any of the other features that leverages that saturation pressure, or in the PVT table itself, you can go to the PVT table and you can check the saturation pressure is here. 2,900. That's the way you would check the saturation pressure. If we go back to fluid definition and we open the reservoir fluid composition card, you see that there is an option to pick a GOR versus bottom hole pressure at the top here. That plots the GOR, and it also gives you kind of an indication of when the GOR starts to increase. Okay, then I'm going to show that one more time. We go here, reservoir fluid composition, and making sure that you have BHP versus time here. And then if we change the GOR to GOR and PSAT, you can basically put in a saturation pressure here. That's that you're forcing to. So essentially the same method that we did earlier. So here I'd like everybody to put in 3,000 as saturation pressure, and then you can go in and click save. Then you have a fluid with the saturation pressure of 3,000 and the GOR of 750. Before that method used to take a little bit of time, so but now it's become extremely fast. Okay, so when we're done with that piece, we're going to go down to what we call the virtual PVT lab right here, which we call simulated PVT study. So we're all the way up here. We're going down to simulated PVT study. Click simulated PVT study, and then we're going to click create new PVT study up here to the left. What we're going to do is we're going to go to either of these. You can go to the CVT or the DLE. Probably the CVT is the best one. And the first thing I'll just tell you is that you can export this into any third party or into Excel, and you will get a report that will look spooky like a actual PVT report. It will look very similar to that. That's a way to virtually create a PVT report. The other task would be to, okay, how do we, or what do we actually think this fluid type is? And I think we earlier talked about the shape. Okay, if it's we know it's an oil, but is it a black oil or is it a volatile oil? And again, here we looked at the shape of this liquid dropout curve. If that is a straight line, then we typically would qualify or classify that as a black oil in general. And that's also something you can go back here and you can see on the PVT table, and that the classification that the software has given us is a black oil. Yeah, very good. I saw there was a question from Edward, just where the file is written after performing export to Eclipse. Okay, so if I export here to Eclipse, yeah, it looks like it should actually come under here on the generated files. So I think I don't know what's going on with the Eclipse export, but it should be up here, Edward. So again, if you had a so if we export this to this table, that's the next thing we would like to do, is just to go here and we would like to export that into Excel. So I don't know if looks like the export is not working, but the export at least would be up here in Excel. I'm a little bit unsure why it doesn't give us an output, but it will be this guy right. I'll follow up on that piece. Some of you also like to use a feature. I'll just show this feature real quick. It's called Simple Material Balance. And simple material balance is a way for you to assume an abandonment pressure and a cumulative producing GOR. So let's say I use something like this, and it will then calculate recovery factors for you with those assumptions. Okay. So let's say you have a DCA forecast of oil and gas. Of course, you'll have a cumulative GOR at the end of history. You might have an estimate of your abandonment pressure, and it's a very effective way for you to quality check what does these recovery factors kind of make sense? These implicit recovery factors from my decline curve analysis. Very good. I'll follow up better on the export there as well. If we change just to the pheasant well right there at the top here, go to PVT feature and we change to pheasant, number 37. We change to the pheasant well right there. We can open it, and we can make the method dry and wet gas, and we can put that to be 0.6, and that's basically what we did earlier, and that will be the way you would initialize the reservoir. That is a dry gas reservoir like this, and all the same things apply there. If you wanted to go in and input a specific or any non-hydrocarbons that's not 0, you can do that as well, and it will go in and predict those compositions for you, just like with as if it wasn't. As if it wasn't. All right. Any questions here? One question I got here in the private chat was just about if any of you need any type of certification or anything for this for PE credits, you can feel free to request those and send them, and we'll make sure to give you all a certificate. And if you need that for any type of renewal of PE, at least down here in the US, it's a lot of that, but just feel free to shoot out an email to us. So if there's no questions, I think we'll round off there to today. The recordings will be distributed later, and you all have a good rest of the day.